Thank you, John. As you said, I will be talking to you a little bit about some arsenic minerals from the Emmons pegmatite, the same one that Al Fauster just told us about. So the first couple slides are going to be kind of reruns. This is a project that I owe a debt of gratitude to Al for, because he's the one that's out there every weekend digging in the pegmatite and finding all these really cool things that we can work on subsequently. So this was really initiated by him and not me. So am I in presentation mode? There we go. So you've seen the map. Al had a slightly different map than I did, but we're just outside of Bethel in the pegmatite complex. There's a picture of the Emmons pegmatite up on a cold winter day last year that Al took. You can't see too many rocks underneath the ice, but somehow he manages to find his way up there and collect samples for us. And you've also just seen this map. This cross section of the Emmons pegmatite. And Al mentioned that it's complexly zoned. You've got the outer wall zone, and then the upper and lower, the hanging wall and footwall intermediate zones shown in yellow. And then the blue is the pegmatite core. And those little black areas are myrolitic cavities that are present within the pegmatite. That's one of those, is that big one that I was sitting in the opening slide. And so the arsenic minerals that I'm going to be talking about come from two of these zones, and they're different in each zone. So I'm going to talk first about the arsenic minerals in the core, and then subsequently about the arsenic minerals in the footwall intermediate zone. So starting with those in the core, we have the most abundant arsenic mineral there is lowlandite. It's an arsenate, and it occurs in masses up to about 8 centimeters. So this picture doesn't show up close where the zone came from or where the minerals came from. I don't have any pictures of those, but this is an older picture from 2013 when PEG 2013 was there, and we had the Emmons pegmatite was crawling with scientists. So it's present generally or oftentimes juxtaposed with lithiophyllite, but there doesn't appear to be any reaction between the two minerals. So they're just happen to be placed against one another. So here's a picture of the actual lowlandite. The field of view here is 4 centimeters across. So they're small, but they're not micro. And they're very abundant. They're close together and generally sort of amorphous, not really crystals. In backscattered electron images on the image on the top left, those little numbers and plus signs are analytical spot where we've analyzed the sample. And the diagram on the bottom right is an X-ray map where the bismuth is in the purple or lilac color and sulfur is in the yellow color. So you can clearly see that the lowlandite is that bright yellow blob down there, although it's fairly dark in the upper left image. And the bright spot under spot number 2 actually has a fair amount of bismuth in it. It turns out that Al has found both native bismuth and bismuthinite in these pegmatites as well. So that's kind of cool. And so here is the SEM analysis of the lowlandite. You can see it's clearly predominantly iron and arsenic. There are some minor elements in there as well. The most abundant one is bismuth at 0.35 weight percent, but there's also manganese, antimony, lead, and tin in these things in very, very small amounts. If we look at the ones in the footwall intermediate zone, they occur along fracture zones between 2 bands of schorl and almonditic garnet. So I don't know if you can see the pointer very well on here, but these bands that are sort of wavy are the bands of schorl and almonditic garnet. And so there's some fracture zones in there where there are some both primary and secondary arsenic minerals. The primary mineral is arsenopyrite, which is an iron arsenate sulfide, and it occurs in fractures in this area. So this is actually not a picture of that. I'm getting ahead of myself. This is a picture of the garnet and schorl in the banded zones. So here is a picture of the arsenopyrite. They're also abundant. They're fairly closely spaced. They're generally about 1 centimeter in size. They can get a little bit bigger occasionally, but not a whole lot. And again, you can see there's quite a few of them in this boulder here. This field of view is 30 centimeters across. So here's a close-up picture of one of those. It's a nice, bright, shiny sulfide. And here's, of course, the conformation SEM analysis of those things. So you can see from left to right, you can see arsenic peaks and sulfur peaks, and then iron peaks, and then the higher end sulfur peaks. Again, we have small amounts of minor elements in these things, but not a lot. Bismuth is present again in this one at 0.16 weight percent. In this case, lead is the most abundant one at 0.60 weight percent. And we also have zinc, antimony, and manganese in these as well. The secondaries are scorodite and arsenosiderite. The scorodite is generally colorless, druzy coatings, and the arsenosiderite occurs as brown crusts. Sometimes you see radiating splays of nice little acicular crystals. Unfortunately, all the pictures I have are in analytical mode. These are the backscatter images for this sample. So you can see the little box on the image on the top left is expanded in the image on the bottom right. And it's these that I will use to show you the X-ray maps again. So again, we see two different minerals. You see those really bright colors in the SEM image up here. Again, if you look at the image to the right here, we've got calcium in blue, and the bismuth in purple. You've got a couple of really bright spots that correspond to the bright colors on the backscatter image. Those would be our bismuth minerals again. And then down in these lower images, you can see calcium in blue, oxygen in yellow. These things are fairly oxidized, which is going to be an important part of our story here toward the end when we talk about what this means. So here is the analytical look at the arsenosiderite. So you've got oxygen peaks and then arsenic, calcium, iron, and arsenic again. So the question is, what does this all mean, or what does this tell us about what crystallizing conditions in the pegmatite? It makes kind of an interesting story. So our observation is that the arsenopyrite bearing fracture had to have occurred after significant solidification of the pegmatite. It couldn't have still been mushy because it's in a fracture zone. So there was clearly brittle behavior. So it's possible, though, then that the lowlingite actually formed prior to the, it is possible that the arsenic mineralization formed prior to lowlingite in the core zone. So if that were the case, that tells us then that crystallization proceeded, the sulfur activity was decreasing, and that would lead to the change from earlier crystallizing arsenic-bearing sulfide, which is, of course, the arsenopyrite, to later forming arsenide minerals, such as lowlingite. And then, obviously, these samples are quite well oxidized, so there was, at some point in this pegmatite's history, significant oxidizing conditions, but there's no way to really determine if that happened as these things were forming or much later in the story, subsequent to crystallization. So we just don't know exactly when that happened. It could have been related to the formation of the arsenate assemblage, or it could have been something much more recent. So I'd be happy to answer any questions if anyone has any.